Okay, so now I want to give you a little example of using the singular value decomposition to perform some sort of image compression. So I'll remind you what I was explaining. The idea is to use the SVD and the leading, let's say, singular values in particular, and their associated singular vectors to obtain some information about an image. So let me go through the code, and as always, I will make this available on the web on UofM Learn. So here, the first thing you need to do is to install the package Pixmap. I think I did not have to install BMP. If you need, you would do the same as Pixmap here, uncomment this, run this. Let me point out, I think this is the first time that I get you to install a package. What would happen is then if you go to the, where am I? Here to your Jupyter notebook, Jupyter Hub, and you went to the top level directory, if you've made another here, when you install a package, it's going to be installed here in this subdirectory R here 4.0 because that's the latest version of R that's running on the cluster, and you can see that Pixmap here has installed as this directory. So be careful not to erase this directory if you're playing around with things. That's just in passing. So anyway, let me get back to this. So I've installed the library Pixmap, and here I call both BMP for dealing with bitmap images and Pixmap, which is sort of allows you to deal with both BMP, TIFF, and a variety of other uncompressed image formats. So to read a BMP, I've taken an example picture, I've transformed it into a gray level image, and I've uploaded it there. So if you're trying to run this code yourself, just upload a 8-bit encoded 8-bit BMP image in levels of gray and replace its name here. It should work. By the way, you see that I'm going to have to re-authenticate. Well, surprising. Why is it forbidden? It shouldn't be forbidden. Okay, so I have my my image, and just as a point of information, my image is an 800 times 1000 pixel image. It has 3 channels, but let's not worry about this. And then what I'm going to use is this function that comes from the Pixmap package that's going to take that image that I downloaded and make sure it is read. It is interpreted as a gray map image. So this is what I store in my image, and then once you've stored an image like this, the function plot becomes able to know this is an image, this is how I should plot it. You'll get a warning message that I don't know where it's coming from, and this is me. This was somewhere, never mind, in Vienna, I think. Took a selfie, so this is an example, okay, of course. And so this is the picture in black and white. So my image, if I put the information, you'll see it's a Pixmap image. The type is Pixmap gray, which is what we want. It's a grayscale image. It's 800 times 1000. I don't really know what the resolution means. I think it simply means that each pixel that you see is an actual pixel, and the bounding box is what contains the image. And since it's 1000 times 100, this is what is happening there. Just in passing, it's frustrating that for image storage, contrary to matrix analysis in general, people think about things the other way around. So this, for us, is an image that has 800 rows and 1,000 columns, and the bounding box here, of course, ends up being the other way, but that's not a problem. Okay, so an image it's an object, so you access the component of the object by using the ampersand instead of the $sign. We've seen this in the past already, I think. And so there's several, let me use the ampersand here so that you can see. If I tab, I'll see what is available. And you can see that there's several components that are available. And what I want is gray, which is where the matrix itself is stored. So I'll extract the matrix, which is simple. And to perform a singular value decomposition, contrary to the example that you will see later when I work it out by hand in the video for the next class, running it in R, even though this is a matrix with 800 times 1,000 pixels, well, 800 rows times 1,000 columns, this goes quite quickly. So let me show you. While the little star is active, it was computing. We're done. So I've stored this in m.svd so that I know that m is my original matrix and m.svd is the one I've applied the SVD to. SVD returns a list this time with several components. And of interest, well, I mean, actually the components, you see what I'm doing here is I'm getting the names. So that's just what the components are, D, U, and V. And then I'm showing you the length of D. So D is the diagonal matrix. It's just the diagonal entries. It's not the whole matrix. It's just what entries make the diagonal of your matrix D in the matrix sigma. And $U is, of course, the U matrix, and V is the V matrix. Okay, so what I'm going to do is what I was saying before, and I'm going to use a function to do that without really struggling. And this function, I'll recommend that you take some time to look at what it does, but I'll go over it quickly. So this function, I'm going to say, compresses the image. It's not really true, but it's close enough. So let's say it compresses the image. So the arguments are going to be an image on which I've used the SVD. So it's essentially, the argument is going to be something like MSVD. Okay, it's going to contain these three fields, D, U, and V. So that's how I expect that the argument will be passed. And N. And N is going to be the number of singular values that I want to keep. So in this particular case, and it's always good to do a little bit of checking. So if the value of N I provide is larger than the actual maximum value that I can use, then what I do is I say, well, it's actually equal to that maximum value. Okay, so that's if I'm trying to say that the R is actually larger than the N in the theorem. And then what I do is simple. I'm just saying I'm going to keep those first N singular values and those first N singular vectors. So what I do is I select from 1 to N in the matrix D, well, I mean the entries in the matrix D, the columns 1 to N, so that means all rows, columns 1 to N in matrix U, and all rows and columns 1 to N in matrix V. Okay. So when you make a function, up to now we've made functions that always return one value, but it can be useful to return more than one value. And if you want to do this, it's often useful. The easiest way to do is to make a list. So I'm saying that the out value will be a list, And what I'm going to do is simple. So I'm going to create an image, which is my output matrix, and that output matrix will have, it's a matrix that has as many rows as U and as many columns as V has rows, because remember, we're taking the transpose of V. And then and so when I create a matrix using mat or vec, it creates a matrix of the indicated size, but full of zeros. And then what I need to do is every time I add this new matrix that I create by taking sigma ui times vi transpose. Okay, so I start out with the matrix made up only of zeros, and then what I do is I add what I had before. So first time around I've only got zeros, afterwards I'm adding things, and what I'm adding is d. So d, that's the value of sigma I times ui times the transpose of vi. Okay. There needs to be a little bit of reshuffling of things, because if you are not careful, you're going to end up with negative values or values larger than 1. So I first make sure that the values are not negative, and if they are negative, I subtract the negative most value, which means I'm simply shifting things to the right until the minimum is 0. And here I'm also making sure that once I've done this shifting, also nothing is larger than 1, and this is, I simply divide by the maximum value in the entire matrix. For information, I also store the number of pixels in the original image, which is just the number of dimensions, the product of the dimensions, and how much pixels I need to transmit if I use this compression, which is how many singular values I'm transmitting plus how many vectors and the size of the vectors I'm transmitting. And finally, just as a quick check, that means the percentage of the original size that is achieved by the compression that I'm doing. And so then what I do, so I need to evaluate this function to make sure it's in memory. And now I'm going to take, so I create a new image in which I put the old image, and what I'm going to do is that I'm going to replace the gray values in this new image by the values I get by using the function. And so let me start with a very simple case. So here I'm using the two largest, and this is plot new image. And I want mtemp. So this is going to be, I'm going to plot what I get by doing this transformation, and what percentage of the original number of pixels I'm ending up with. So when I do this, I'm using 0.5% of pixels, but clearly this is not looking very good. Let me put everything in the same. I put it in different so that I could explain, but let me put everything here. Now let me do 5. So 5. So I'm going to keep the 5 largest singular values and their associated vectors. So you can see it's already looking not that bad. And this is with, this is with 1.4% of the original number of pixels. This is what this recomposition has given me. So let's do 20. So 20 is 5.6% of the pixels. And now you're starting to really see the image. It's still quite pixelated, but it's looking good. And essentially, let's look at this. 50, I have 14% of the original image, and you can see that this is getting quite satisfactory. Okay, I can still see quite a lot of pixels, but most of the information is there. And so what I have done here is I have lowered the amount of information that I needed. I'm using just these 50 singular values and the associated 50 right and left singular vectors. I have encoded the image, and you could raise the number all the way to 800, but at some point the image, let me do 150, the image becomes barely discernible from the original one. Of course, here the computation is longer, but you can see with 150 singular values, this is looking much better.